So we're going to practice the Descartes rule of signs, and yeah, just kind of power through all of this. So the first thing to notice is there's no constant. And since there's no constant in this problem, you can examine what would be the greatest common factor, and that was the x squared. So that tells me that we know there's exactly 2 zeros at 0. So the next thing to do, I guess you could start by writing your chart if you wanted to, positive, negative, 0. So we already know that there's going to be 2 0 roots in that imaginary. So what I would do, this is my opinion, is I would start by looking, not even doing any arithmetic, just seeing that it's negative to positive to negative to positive. So as I look at my sign changes, that there's 1, negative to positive is 1, positive to negative is 2, negative to positive is 3. So there's 3 sign changes. So I'll write that down, except that doesn't even look like a 3. Let's fix that. And remember that we go down in in skipping numbers would probably be the best way to say this, that there's either 3 positive roots or 1 positive root. Because remember, an odd function has to cross the x-axis because it goes, the end behavior, let me draw that real quick, goes like this. And an odd fifth degree might have 4 turning points, but, something like that. But if you put an x and y axis somewhere, it doesn't matter where you put it, it's got to cross the x-axis somewhere. Could be a negative, could look like this. I'm only putting 2 turning points, I don't really know why. But now what you need to do is investigate, what if it was f of negative x? I went ahead and wrote those down already. And just think about, okay, well, if you have a negative to an odd power, it stays negative, but times this negative, turn that back into a positive. Negative to an even power, it's back to a positive. Negative to an odd power is a negative times this negative, it's positive. And then a negative squared is a positive. So we're looking at a positive to a positive to a positive to a positive. There is 0 sign changes. So that first graph I drew for you earlier, this one over here, this one's definitely wrong because there's no way across the x-axis based off the Descartes rule of signs. So we already know that there are 0 negative roots. So let's finish that chart. Okay, well, the first one that we set up is there were 3 positive, 0 negative, 2 imaginary. How many are left over for imaginary roots? Well, there's 5. Well, we've already gotten 5 by the fundamental theorem of algebra, so there's none left over to be imaginary. Now, the next time I do this, there has to be 2 0 roots by the constant rule. There has to be 0 negative roots by the Descartes rule of signs, but you could have 1 positive root. So if there's 1 positive with 2 0, how many are left over to be imaginary? 2. And this really gets down to the nitty-gritty as to why we go down in increments of 2, because imaginary numbers have to happen in pairs of 2. So this is your sign chart. Well, I shouldn't call it a sign chart. A chart that explains the number of roots. So now what they do is they want you to go to a graphing calculator, plug it in, and see which one works. So I'm not going to do all of that. But what you'll notice is you'll either find a problem that looks like this, where it only crosses the x-axis once, or you'll have a graph where it crosses the x-axis and then comes back down and then crosses the x-axis again to make its end behavior. So I'm actually just going to go to the answer key because I trust that you guys can type this into a graphing calculator and see which one's which. And according to the answer key, we are looking at the 1, 0, 2, 2 problem. Alright, and this guy also does it slightly different where he puts the numbers above where I wrote it off to the side. And I'd even talk about imaginary being 4, 2, or 0. But it was even impossible for imaginary to be full. Excuse me. Because we already knew that there were 2 0 roots. Well, that only left 3 more roots. So I would even argue with the person who made the answer key and say, why would you write down 4 imaginary when that was not possible? And, you know, I'm sure I would probably agree with whatever he says as well. But maybe I need to move a little bit faster to make sure I get this done. So looking at the constant, there are 0 roots at 0 because it crosses the crosses the y-axis at 1, so it doesn't cross at 0. So now I'm looking at this sign changes negative to positive to negative to positive to negative. That is 1, 2, 3 sign changes. I must have said that wrong. Let me fix that right there. Positive, positive. So positive, positive does not change. So that means 3 or 1 positive roots. So then a little bit of arithmetic. Now, as you get more practice with this, I don't think you'll be showing as much work as I am right now. At this stage, though, I'm just trying to explain every little thing. So negative to an even power goes back to being positive times negative 2. It's still that. And then the negative to an odd stays negative. This one would, x squared would become positive, but then times negative 7 minus 4x plus 1. So negative, 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 positive. So we do have one sign change. That means 1 negative root. So I think we have enough to make the sign chart. And I'll go back to purple. So I'm going to try and squeeze it right here. Positive, negative, 0, or imaginary. Could have 3 positive with 1 negative. We already know there's 0. And then how many imaginaries are left over to get a polynomial? That's 4 degrees. And then the other possibilities, we could have 1 positive. We still have to have 1 negative. It has to cross the x-axis and the negative based off our math, leaving 2 imaginary to get up to the fundamental theorem of algebra. There you go. I'm going to do one more, and then I'm going to share the answer key. So again, the directions ask you to use a graphing calculator to see where it crosses the x-axis and which one we're looking for. So again, there's a coefficient, or sorry, there's a constant there. So there are 0 roots at 0. So then we're looking at positive, negative, positive, positive. That is 1, 2 sign changes. So that's 2 or 0 positive. And I'll show you a little bit faster with the negative q of negative x. Because some of you are smart enough to not show that work, that you could just say, oh, a negative cubed is negative. A negative squared is positive times negative 3 minus 2x plus 1. So that's negative, 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 positive. That is 1 sign change. So there's 1 negative root. So make your sign chart. So we already know, without a shadow of a doubt, that there are 0 roots at 0. There could be 2 positives with 1 negative, meaning that there's none left over to get up to a cubic. Or there could be 0 positive with 1 negative. Has to cross the x-axis somewhere, because it's an odd function, leaving room for 2 imaginary. So again, I'm going to go back to the answer key. and they highlighted the correct one. And this is his math. It's a little bit different than mine, but still does work. And you can see he moves a little bit faster with his answer key. I don't know if you're quite there yet, but you will be. So when you use a graphing calculator, you see number 2 crosses to the left of the origin, to the right of the origin, and then there's 2 imaginary roots. This one crosses to the left but not to the right, so it has to have 2 imaginary. And again, feel free to pause the video and see if you can get it on your own. Notice number 4, there is only one possibility. It had to cross a positive, a negative, and a 0, meaning there's no room for an imaginary root. And number 5, there were 2 possibilities, and the one that works is the 1 positive, 1 negative, and 2 imaginary. And you should be ready for the homework. Just feel free to pause the video or rewatch it, and hopefully you understand. If not, please email me or come to class with questions.